If you studied the Carnot cycle in thermodynamics, you may sometimes have wondered why the adiabat is steeper than the isotherm. So in this video, I'd like to attempt to try to provide a basic explanation for why that is. So to start off, let's just review a couple of tools that we will need as I go through this explanation. First is the ideal gas law, which is that, of course, the product of the pressure and volume of an ideal gas is equal to the number of moles of the gas times the gas constant times the temperature in kelvins. So we're going to be needing that, where in the case under consideration, I just want to emphasize that these two are constant. So the number of moles is not changing. I have gas contained in a container. Number of moles is not changing, and the gas constant is always 8.31 joules per Kelvin. And the other thing we need is that the temperature is actually a direct measure of the kinetic energy of the particles, and in an ideal gas, kinetic energy is all the energy there is. There's no potential energy between the particles. So we can say that the internal energy of an ideal gas is a scaled measure of temperature. So whenever you think of temperature, think immediately of how fast the particles are moving, namely the internal energy of the gas. So that's 3/2 times the Boltzmann constant times temperature. So again, take note that this is all constant, and that is the internal energy of the gas. And finally, the third thing that we need is the first law of thermodynamics, which states that the change in internal energy of a gas is equal to the amount of heat supplied to the gas plus the work done on the gas. So if I were to supply heat to a gas, the particles will start moving faster and hence increase its internal energy. And if I were to do work on the gas, if I were to push on it, as the piston compresses the gas, the particles will come off with a greater momentum and hence increase their internal energy and their temperature. So just take note that as we do this, we can switch between work done on the gas and work done by the gas, such that if I wanted to change this to work done by the gas, it would just be minus the work done on the gas, right? So if I did a certain amount of work, 10 joules on the gas, that would increase its internal energy by 10 joules. But if the gas itself were to do work, it would lose 10 joules of energy. So that's opposite. And likewise, if I were to remove heat from the gas, then that would be minus the heat supplied to the gas. So we might use that interchangeably in our discussion. So this is the first law. Alright, so let's get to it. So I will start with let me start with a picture here. So I'm going to be having a container. Let me just draw the PV diagram first. So here's the pressure volume diagram for what I'll be looking at. and I'm going to start by looking at the compression of a gas under isothermal conditions. So on an isotherm, let's look at what we have for an isotherm. For an isotherm, the temperature is constant. So no change in temperature. That's what the definition of an isotherm is. There's no change in temperature. So if we look back at the gas law that we wrote down earlier, if the temperature is constant, that means the product of pressure and volume everywhere is constant. So I can say that if I were to start with a state P1 V1, then if I end up in the second state P2 V2, those two products will have to be equal. So let's start down here at P1 V1. Oops, sorry, this is V1, this is P1. And I end up at a different state of the gas P2 V2, and I'm compressing the gas, so the volume will decrease like so. So I'm going in that direction and I'm compressing the gas. Alright, so its volume decreases to V2 while the pressure increases to P2. Right, because if you decrease the volume, particles get squeezed together, they collide with the walls more often, they come off with greater kinetic energy, and so you get a larger pressure. Now let's compare that to what would happen in the case of an adiabatic compression. So over here, I'm going to look at what happens to the adiabat. So I'll start by writing down the first law for this case. Now, the definition of an adiabat is that there's no heat supplied to the system. Right? That's what an adiabat means. No heat supplied. So in my first law, I can get rid of this first term here. No heat supplied. Therefore, the change in internal energy of the gas is equal to the work done on the gas. Now, I am in fact doing work on the gas. Therefore, the work done on the gas is a positive quantity, which means that the internal energy of the gas will increase. The change in internal energy is positive. The internal energy of the gas increases. Now let's go back to here and look at my equation relating the internal energy and the temperature. If the internal energy increases, what that must imply is that the temperature increases, because this term here in front of the temperature is actually constant. So indeed my temperature has to increase because of that. So because of that, I have a positive change in temperature, right? And as a result of that, let's go back to the gas law. As a result of that, if I have a positive increase in temperature, that means this product, right, I'm not worried about what goes on individually in P and individually in V. Just take a look at this product here. this product PV has to also increase numerically because the temperature has increased, therefore the product PV has to increase numerically. So the change in this product PV also increases due to the gas law. Now contrast that with the situation here on the isotherm, where we found that the product actually stays the same. So what does that imply? Say I squeeze. Now these are two different experiments, okay? So I have the isotherm experiment here, and I did it, so I'm all set. And in the adiabat, I have a very well insulated piston where I squeeze it without any heat gained or lost by the system, and I end up, say I squeeze it to the same volume. Okay, so I start right here. So for the adiabat, I start in the same place. So P1 V1, and I want to end up at the same volume, V2. Okay, so here's my initial, and when I finally end up in the second state for my adiabat, this number, whatever this product PV is, it has to be greater than what I started out with because of this, because the temperature is higher, so the product temperature is higher, so the product PV has to be larger, as we discussed. So I'm going to end up at the same temperature as with the isotherm. So I'm going to end up at a different pressure. Okay, I can control the volume, right? I can control how far in I'm pushing the piston, but I can't control the final pressure that I end up with. Therefore, it must be that since P1 V1 was equal to P2 V2, I have that P2 prime V2 is greater than P2 V2, because these two quantities here are equivalent. This P2 V2 being the point on the isotherm change here. So with that, I can cancel the V2s here, and I find that the adiabat pressure, let me just make sure we understand the distinction here. This is the adiabat pressure, whereas this P2 is the same isotherm pressure. That I ended up with when I did the isothermal compression. So the adiabat pressure for the same volume, right? For the same volume, I'm pushing them to the same volume. So I'm going to draw a vertical line here to make sure we know that we end up at the same volume. Has to be greater than that of the isotherm. So I'm going to end up at some greater pressure, but for the same volume, the isotherm. So if I join those two, you find that always for quasi-static processes, we're not going to that terminology now, but you can see that it is always the case that the adiabat is steeper than the isotherm. Right. So, of course, there's a somewhat more simple qualitative argument. Well, I shouldn't say simple. There's this qualitative argument that we can make to arrive at the same conclusion, which is that by looking at start by looking back at the isotherm case. Well, but I just want to say that for the quantitative argument, we're done here. So this shows that why the adiabat and isotherm, the adiabat is steeper than the isotherm. So for all intents and purposes, we're done. But just as a further argument, we can look at the first law for the isotherm. So the isotherm, I have that change in internal energy is heat supplied to plus work done on. And for an isotherm, there's no change in temperature. Because there's no change in temperature, there's also no change in internal energy, right? Because if this whole thing is constant, then internal energy is constant always. Doesn't matter what my pressure and volume of the gas is, I'm keeping the temperature constant. So therefore this quantity here goes to 0. So the heat supplied to is minus the work done, right? Just bring the heat supplied to this side. And what I find in that case is that the work done on is the heat taken away from the system, right? So that stands to reason, because as I'm applying, as I'm forcing the piston in, the particles would naturally move more quickly. Now, if that were the case, the temperatures will start to increase. So to keep the temperature constant, I need to take heat out of the system, hence remove heat from the system. So whatever work I did on the system, I'm removing from the system, so that the internal energy of the particles stay constant to make the temperature stay constant. So if that were the case, well, as heat is being expelled from the system, I'm doing actually less work on the gas, right? It's making my life easier. I can push the gas in more easily because particles are not hitting the piston as hard, and so I do less work. So I need less force on the piston, so less work done. This is as opposed to the case for the adiabat, where I'm not actually removing any heat. I'm not putting any heat in, but I'm not taking any heat out either. So I guess we could say that there's no heat taken out. So the particles are moving faster and faster, the temperatures are increasing, so they're moving faster and faster, and there's a greater force exerted on the piston, so I get a greater amount of work done as I go along. I need to overcome that greater force. So we see that that is indeed the case here, where for the isotherm, the area under the graph, which, if you recall, the area in the PV diagram is actually the work done on the gas, is actually less in the adiabat. So for the adiabat, I need to do this extra work over here, and so that puts the adiabat steeper up above the isotherm, so that I can get in that extra area corresponding to the extra work that I need to compress a gas under adiabatic conditions, because I'm not taking any heat out from the system, hence I'm not getting any help, making my life easier pushing the piston in, right? Having looked at the case where the gas is being compressed, we will now turn our attention to the case where the gas is expanding. So I'll once again have my PV state diagram. And now let's look at the isothermal case first, where I will have some starting volume, V1, and some starting pressure, P1, and as I allow the gas to expand, its volume will increase to some volume, V2, and as it does so, the pressure drops because as the volume gets bigger, particles have more space to move around, they don't hit the walls as often. So I end up with this isothermal expansion here. This final state is my state P2V2, P1V1. I won't go through all the rigorous details one more time, but we can take a look at the case of the Adiabat. If I look at the Adiabat, very quickly we'll see that here's my first law. Increase is heat supplied to the gas plus work done on the gas. Since it's an adiabat, there's no heat supplied to the system, therefore change in internal energy is the work done on the gas, which I can also write as the work done minus the work done by the gas. And the reason I'm writing it that way is because in fact the gas is actually doing work on the environment, because it needs to do work to expand. And since work done by the gas is a positive quantity, I'm taking minus a positive quantity, so the internal energy of the gas actually decreases. And that makes sense too, because as the gas expands, it's going to start to cool down because the particles won't hit the walls as often, so they lose kinetic energy, and hence the temperature now decreases. So I actually do want to end up at a lower temperature, meaning a lower product of PV. If you look back to our previous discussion, so very quickly we can see now that in an isothermal expansion, the gas ends up at a lower pressure for the same volume as the isothermal expansion. For the adiabatic expansion, the gas ends up at a lower pressure. That's my adiabat. And so we see once again that the adiabat is again steeper than the isotherm.